Hello, my name is Chris Fisher. Thank you for your interest in our presentation. Today I will be presenting an ACT-R model of order effects that I developed with my colleagues Lorraine Borghetti, Joe Haupt, and Chris Stevens. Let's begin by defining order effects. An order effect occurs when a response probability depends on the order in which stimuli are presented. Order effects are interesting because they violate the commutative law of classical probability theory, which states that the probability of A and B must be equal to the probability of B and A. In other words, order does not matter. In addition, order effects indicate that cognition is context dependent. I will frame the discussion of order effects around an example reported in Long et al. 2014. This example is based on a Gallup poll in which respondents were asked two questions. Do you think Bill Clinton is generally trustworthy and honest? And do you think Al Gore is generally trustworthy and honest? The joint probability tables for both question orders are presented on the right. We can check for the presence of an order effect by computing the element-wise differences between the two tables. The element-wise differences between the two tables is presented on the right-hand side. If no order effects are present, the expected difference in each cell would be 0. However, there is a clear order effect present in the data. You may have also noticed a symmetry in the diagonal cells and off-diagonal cells. I will return to this pattern shortly. One popular account of order effects is the quantum probability model. The quantum model is an alternative theory of probability based on a set of axioms that differ from those in classical probability theory. In the quantum model, events are represented as basis vectors in an n-dimensional Hilbert space. A person's belief state is a linear combination of basis vectors. The probability of an event is computed as the projection of the belief state vector onto the basis vector that represents the event in question. An important concept in the quantum model is compatibility. If events are compatible, they can be represented with a common set of basis vectors. In this case, the quantum model agrees with the predictions of classical probability. However, if the events are incompatible, then the events cannot be represented with a common set of basis vectors. Instead, a new set of basis vectors for the incompatible events are found through rotation. Importantly, this allows the quantum model to violate the commutative law and produce order effects. A critical property of the quantum model is called the QQ equality, which imposes a symmetrical relationship on the pattern of order effects. The difference table on the right-hand side illustrates the QQ equality. The first Q value is found by summing the diagonal elements, which equals 0. Similarly, the second Q value is found by summing the off-diagonal elements, which again equals 0. As you can see, the empirical data from the Clinton-Gore example approximates this pattern. Long and colleagues found support for the QQ equality in several experiments in a large body of Gallup polls. The primary goal of this presentation is to address the question whether ACT-R can produce order effects and satisfy the QQ equality. ACT-R is a cognitive architecture, which is a formal framework for developing and testing unified theories of cognition. Order effects present an interesting challenge for ACT-R because it was not developed with order effects in mind. This means that ACT-R must account for order effects with existing mechanisms. As a high-level overview, we developed a memory-based model of order effects in which judgments are based on retrieved instances stored in memory. Order effects emerge from ACT-R's spreading activation mechanism. In essence, the answer to the first question spreads activation to related concepts during the retrieval of the answer to the second question, thereby changing the response probabilities for the second question. Without the spreading activation mechanism, ACT-R satisfies the commutative law and fails to produce order effects. Our main finding is that the pattern of order effects in the QQ equality depends on the ratio of chunks for true and false statements. In some cases, no order effects are predicted, while in other cases, order effects are predicted. Similarly, Q values are 0 or close to 0 in many cases, consistent with the quantum model. However, in other cases, the Q values are moderately to extremely large, marking a divergence from the quantum model. Each chunk consists of 3 slot value pairs, one for the name, one for the statement, and one for the truth value of the statement. The example on the slide is a chunk for Clinton, who said statement S, which was false. For simplicity, we assume each statement is unique. After encoding the question, a retrieval request containing a slot and value for name is submitted to declarative memory. On the slide, the retrieval request is for a chunk that has the name Clinton. The retrieval set, denoted with an uppercase R, consists of all chunks that match the retrieval request. If the retrieval request is for a chunk about Clinton, then R consists of all chunks for Clinton regardless of statement and truth value. The response rule is quite simple. Suppose chunk CR is retrieved. If CR contains a truth statement, the response is yes, otherwise the response is no. The chunk in the retrieval set with the highest activation level is selected for retrieval. Activation for chunk M has several components. Beta is a base level constant which shifts activation up or down. Sm is spreading activation for chunk M, and epsilon M is normally distributed error. In the model, the chunk retrieved from the first question is stored in the imaginal buffer. Activation spreads from this chunk to other chunks with a matching truth value. In the spreading activation equation, X is the number of truth values across declarative memory that match the truth value of the chunk in the imaginal buffer. Gamma is the maximum association parameter, and Q is the set of slots in the chunk of the imaginal buffer. As shown in the equation, activation is divided among matching truth values. Thus, spreading activation decreases as the number of matching truth values X increases. On the first question, the probability of a yes response depends on the ratio of chunks with a true value statement relative to all chunks in the retrieval set R. We will divide the retrieval set R into 2 subsets. W yes is the set of chunks in R containing a true statement, and W no is the set of chunks in R containing a false statement. The probability of responding X to the question about person P is given by the softmax function on the right. Recall that beta is the base level constant and sigma controls the level of noise in the activation values. Because beta and sigma are constants, they can be factored out of the numerator and denominator where they can be canceled. This means that the probability of responding yes to the first question simplifies to a ratio of true to false statements for the person in question. The equations can be rewritten to reflect the ratio of true to false statements. We define TC as the number of true statements for Clinton, FC as the number of false statements for Clinton, TG as the number of true statements for Gore, and FG as the number of false statements for Gore. For example, if there are 3 true statements and 1 false statement for Clinton, The predicted probability of yes is 0.75. The response probability for the second question includes a spreading activation term. After some algebraic manipulation, we obtained a spreading activation term on the right, where x is the number of matching truth values across declarative memory. As an example, the second question represents the probability of responding yes to the question about Gore, given a yes response to the question about Clinton. The spreading activation term scales the value Tj, which increases the probability of responding yes to Gore, thus producing an order effect. Now I would like to summarize some of the key predictions for order effects. I will define E as the order effect and use subscripts to denote the cell in the difference table. When the ratio of true to false statements is equal for Clinton and Gore, there is no order effect for yes-yes responses and no-no responses. However, the order effects for yes-no responses are the negative of no-yes responses. As a special case, when the ratios are balanced, or 50-50 for each person, all order effects are zero. In many other cases, when the ratios differ for each person, some degree of order effect is predicted. The ACT-R model predicts that the QQ equality will be satisfied under the following two conditions. First, the QQ equality is satisfied if the ratio of true to false statements is equal. For example, 1 out of 2 statements are true for Clinton, and 2 out of 4 statements are true for Gore. Second, the QQ equality is satisfied if the ratio of true to false statements are complementary and the total number of chunks for each person is equal. For example, 2 out of 3 statements are true for Clinton, and 1 out of 3 statements are true for Gore. We performed a simulation to determine the distribution of Q values across a wide range of conditions. In the simulation, we enumerated all permutations of TC, FC, TG, and FG for values ranging from 0 to 6. The histogram on the right shows that the bulk of the Q values are near 0. 77% are between negative 0.1 and 0.1, and 68% are between negative 0.05 and 0.05. Some violations of the QQ equality are quite large. In many of those cases, the ratio of true to false statements for Clinton and Gore were different. The violations were quite large when one of the values was 0. In this research, we developed a memory-based model of order effects within the ACT-R cognitive architecture. Spreading activation was responsible for producing order effects. Activation from the chunk retrieved for the first question spreads to other chunks, which changes the probability distribution for the second question. An important finding is that order effects and Q values depend critically upon the ratio of true to false statements for each person. Typically, Q values were small, but were large in some cases, marking a divergence from the predictions of the quantum model. We presented an ACT-R model of order effects as a proof of concept. Many of its predictions appear to be plausible. However, the predictions ultimately must be tested against data from an appropriately designed experiment in which the contents of memory are manipulated. We are currently in the process of designing experiments to test many of the model's predictions. For example, we will include conditions that predict both small violations and large violations of the QQ equality. We are also investigating the property of the model under relaxed assumptions. For example, the base level constant could be drawn from a distribution to reflect variation in encoding strength. Thank you for your interest in our presentation, an ACT-R model of order effects.